An object of mass 50 kilograms accelerates from a velocity of 2 meter per second to a velocity of 10 meter per second in the same direction. What is the impulse provided to cause this acceleration? So the question seems a little tricky once you realize it. Well, what is the one formula of impulse we know? Well, it is the force is equal to the change in momentum over time. This is what we know. And this is the change in momentum. This is what we talk about when we say impulse. Essentially, impulse is the change in momentum. If a momentum is changing, that's impulse, right? How do we figure out the change in momentum? Well, momentum itself is mv. That's how you calculate momentum. How do you find the change in momentum? Well, you have to find two different momentums and subtract them, right? Now, why two different momentums? Let's take another look at an equation we already know over here. Acceleration is the change of velocity, v minus u, over t. Why is it v minus u? Well, this is the final velocity minus the initial velocity. So what your number is now, it could be velocity or anything. If you want to change, you take the final value and take away the initial value from it, right? That's my change. It's always a final minus an initial. So just the difference of two momentums. Well, I take the final momentum and the initial momentum. So can I calculate my final momentum and subtract my initial momentum from it? How do I calculate my final momentum? Well, if I take a closer look, this is my final velocity. So m times v, where I put this value in there, will give me my final momentum. This is my initial velocity, and n times v of my initial velocity will give me my initial momentum, right? So let's put that in there. The change in momentum is just the final momentum minus initial momentum. All right, so that's 50 times 10, because it's 10, minus 50 times 2, because it's 2. That's my calculated my initial momentum, right? And this is 500 minus 100. That's 400 Newton seconds or kilograms meter per second. Either is fine. They're using Newton seconds. B is my best answer right now. An object is acted upon a 3 Newton force and by a 4 Newton force. Each diagram shows these two forces. So we see that it's 3 and 4, 3 and 4, 3 and 4. They seem to be all perpendicular. Which diagram also shows the resultant of these two forces? Well, how do you figure out the resultant, right? So let's take case A. This is my 3 Newton force, and I know my 4 Newton force is over here, like this, right? How do I calculate, or what is the way about it? What is the technique? Well, it is the head to tail rule. Head to tail rule. What is it? Well, for the second vector, attach it to the head of the first vector, like that. And once you have all the vectors aligned in one sequence, no matter how it goes, you label the start of the vector, where the first vector's tail, essentially, where everything started, and end to the head of the final, or the last vector. And you just join them. That's the worst vector I've drawn, so I'll redraw it. It's still pretty bad. Can't seem to draw it. I still think I won't be able to, but good enough. This is my resultant vector, right? What diagram is doing the best job of this? Well, take a look. X looks a lot like our picture over here, right? This is my resultant. And it makes sense. If an object is over here, if someone's pushing it to the right and someone's pushing it down, it's going to move that way, right? This is the resultant of that vector, not that, not that, and not that. Which diagram shows the magnitude and direction of the resultant R of the two forces F1, F2? We have F1, they're all the same, and F2. So essentially, this is F1. I want to take F2. I won't draw F1 again like I did in the previous question. I'll take F2, and I'll just move it in front of F1 where it's kind of like, why am I doing it like this? I can do it any way I want as long as it's satisfying the head to tail rule, which is that the end of this vector should meet the head of the other vector, right? So if I do that here, that's what F2 would look like, pretty sure. And the resultant would essentially be this vector, and seems like R is already doing it, right? Or in A, it's already, that's what's happening. Look at F1. The direction of R is opposite. And sometimes you'll see that, and sometimes that will be the answer. But the question won't be asking for the resultant. And we'll see that question. C just looks like a nice triangle, but it's not making any sense. Look, if someone's pushing it like that, some object, and someone's pushing it down, what would be the effect? Won't it go somewhere like that? Here, or maybe here, or maybe here, somewhere around this region? It's saying this, it's going like that. That makes no sense. Why would it? Right? R seems much more plausible. And look at B. If someone pulls it, an object in this direction, and the other one pulls it in this direction, will the object go like that? No, it won't. Similarly with D, same issue. A is our answer. Diagram shows the only two forces F1 and F2 acting on the object. The magnitude of each force represents the length. So the length is matching. The resultant force acting on the object is R. There is some resultant force acting on it, and it's probably going to look like somewhere like that. This is pretty long, so maybe it's a little more like that, right? Okay, which vector diagram shows the force F1 and F2 added to produce R? Right, straightforward. I'll take this vector, I'll put it over here. Let's try that. Now I can do whatever I want. Again, I can redraw this, but I'll just it's easier to just take this and just put it over here, because it'll automatically do the head to tail thing, right? I don't have to draw everything from scratch, right? I have to work on my time because it's an MCQ. Something like that. I'll try to match the length as best as I can. This is my start, that's my end. My vector is BAM, right? That should be R. I'll match this picture with whatever is given to me below. All right. Now, don't focus on F1 and F2. They all look weird. They've done it randomly, and they're probably trying to do it in a way where they're trying to confuse you, right? So let's just match R. That looks a lot like what I had, right? And that's my answer. This is it, right? Now, I can actually answer this question without reading the question. How? Because I'm looking for I need to know if I'm looking for the resultant or something else. If I'm looking for the resultant, let's take a look at A. Does that look like the resultant? Well, it seems to me F1 and F2 are not joined head to tail. If this was joined head to tail, either in front of F1, F2 should have been here like that, or you could do it the other way around, where in front of F2, the F1 vector should have been here going like that, and R1 would be the resultant when you connect the two together like that, something like that, I don't know, right? So this is not drawn accurately. It makes no sense how it's drawn. If it looks pretty to you and that's good enough for a good answer, it doesn't work like that, right? Let's take a look at B. Well, F2 and F1 are drawn correctly. This is what I meant when I said F1, if it's connected here, will give you something similar. It's drawn correctly and it looks good. The only problem is, technically, isn't this your start? Isn't this your end? Shouldn't this vector point the other way? So B is wrong, right? All right, moving on. And this is why D is actually the answer, because this is matching over here, and this matches this vector, and R is drawn correctly. And A and C is just, it's still wrong. So this is still wrong. And this is even more wrong because it's just like weird that way, right? So C is automatically out because of the same reason as why A is out. D is our answer. All right, I like this question. The diagram shows an incomplete scale drawing to find the resultant force of two 10 Newton forces acting at the same point. So there's a box over here, someone's pushing it by 10 Newtons here, another one is pushing by 10 Newtons over here. Someone's done us the effort of half solving this question by not the head to tail rule, by using a parallelogram. So they essentially took this line, made one over here, another parallel line to this, made it over here, and it's connecting over here. And why they're doing it differently? Well, fun fact, if you try to draw this vector over here and try to connect it, you'll get the same response. It's just the same thing, right? Okay, so what are the magnitudes? So one thing you can do is just put a scale over here and measure it. Now, for the answer on your scale to be right, this has to be 10 centimeters as well. If you put your scale over here, it should read, the length should be 10 centimeter, or so whatever answer comes into centimeter, it'll do that. The second way you can do it is, let's say if this is 5 meters or 5 centimeters on your scale when you put it over here, and when you measure this, this comes out to be 7 centimeters, right? Or maybe 8 centimeters. Let's go with 8 centimeters from here to here. Well, how much is this length then? Shouldn't this be 16? Does that make sense? If this length is 5 centimeter on your scale, this length which I haven't drawn from here all the way up till here, connecting it, shouldn't that be 16? Oh, if you measure it, it comes out to be 8 centimeter. That means वो length actually 16 newtons की होगी. इस वजह से, that is why the measurement is coming out to be 8 centimeter. So you convert it back. Easy. But the good thing is you have options given to you, so you don't have to resort to either of the two ways. This is very important when you need to do it graphically, right? So it's important that you should know how to do this. But if you can't, if you don't need to, how do you do it? Well, like the options given over here. So what could this length be? Well, it has to be greater than 10, right? How it's arranged. So B and A are out, and you're left with C and D. Well, can you ever get 20 over here? Well, to get 20, the only way you can get 20 in this situation is when these two vectors are lined up exactly. So their entire length, like that, is 20, right? So this will never be 20. It can be close to 20, but never be 20. So you're only left with one viable option. It's C. That's the best bet. And you can try it. You can put a scale over here, whatever value comes out, let's say 5, and then measure this, right? So whatever conversion is over here, do the reverse conversion, and this length will be 18, right? Let's move on. A stone of mass 0.12 kilograms is fired. The velocity of the stone changes from 0 to 5 in 0.6 seconds. What is the average force acting on it? Simple as plugging it into the formula. The force acting on it, the average force acting on it, is the change in momentum, which is also the impulse over time. So we don't know the change in momentum. We can figure it out. The mass, so it's mv2 minus mv1, like we talked about, over time. What is mv2? Well, mass is 0.12 times the velocity. The final is 5. The initial is, which is 0. Well, that's easy. 0. Entire thing becomes 0 in a span of 0.6 seconds. This will equal 1 Newton. Newton because it is a force, right? A is our best answer. Car is moving in a straight line on a level road. Its engine provides a forward force of the car on the car. A second force of equal size acts on the car due to the resistive forces. What is that force? Probably drag force, right? What statement describes what happens? The car changes direction. Well, it's against it, right? If a car is moving like that, the resistive forces like that. So it's gonna try to slow it down. The car moves at a constant speed. Well, are they equal? Forward force on the car, a second force is equal size, right? So it's at equal size, equal speed. It's at constant speed because the two forces are equal. So there's no net acceleration, there's no resultant force. So yeah, this is correct. Car slows down, nope, they're equal. Car speeds up, nope, they're equal. Car changes direction, nope. B is our answer. Tension is another word for the force in a string. This is called tension. What would this tension be if this is stationary? This is just hanging. So the force experienced by the wire is equal to the weight of this object. The weight is, well, that's easy, 20 times 10, which is g. I'm using the formula mg is the weight. So this is just 200. So the tension has to be 200 over here as well. Correct answer is D. Ship travels due north through still water at a speed of 20 meters per second. North, right, I see that. It enters a channel where there is a current from west to east, so towards the right. The speed of the current is 20. Going up 20, going right 20, which diagram shows the resultant. Going up, going down. So they've connected it over here like that, right? But it's not head to tail. But it makes sense what's happening to the ship, which is over here but not shown. What we can do is move this vector over here like that. So let's do it for A. It's going to be something like that. And the resultant vector is going to be like that. This is the start. This is the end. Should be a pretty good habit by now. And notice the direction is like that, right? And it makes sense because if a ship is trying to go like that, up, and the water is pushing it towards the right, is going to end up moving like that. So pretty clear. So A is wrong. Essentially, I have to find what I've drawn in green. B is wrong. Let's look at the other two. All right. It looks like C is what we were expecting. They haven't drawn this part correctly, but they've gotten the right result by drawing a parallelogram. But stick to the head to tail rule. You've already know your answer from above. This is how you do it. Don't get confused with the rest of this gibberish. They're just putting in there because they're lazy to remove it. You know how the resultant vector is. I mean, even before you do it, you can just do it from common sense. This is pre-physics information, right? You know something's going to move like that if, if the board is moving like that and it's also being pushed towards the right. So it keeps moving up and right. Correct answer is a C. Hammer is being used to drive a nail into a piece of wood. The mass is 0.15 kilograms. The speed when it hits is 8. And the time for the hammer's head to stay in contact is this much. Looks like an impulse question already. A little more down. Okay. So the hammer's head stops after hitting. So it's moving, then it's not. Calculate the change in momentum. Well, the change in momentum to us is given by, which is the impulse essentially. Change in momentum, which is impulse, is final momentum minus initial momentum. You can write 2 or 1 or whatever. Does not matter. All right. So the final momentum is 0 because it stops. That's 0. You're left with initial momentum, which is negative mass velocity. The mass is 0.15 times the velocity, which is 8. This is equal to 1.2 Newton seconds or kilograms meter per second, right? Sorry, negative, right? Now they're asking for the change in momentum. The negative implies what? The direction. But the value is 1.2. So let's just quote the value. It is 1.2 Newton seconds or kilograms meter per second. This is done. Now, what does the negative sign imply? Well, the hammer's head, let's say this is a hammer's head, is moving down. The change in momentum is actually upwards, which makes sense because this slowed down, this stopped, right? Let's move on. The next part says, state the impulse of this that is given to the nail. Well, that's a change in momentum. That's the same as that. So the impulse is 1.2 Newton seconds. Calculate the average force acting on the hammer. That's pretty easy. We have already done half the equation. Average force is just the change in momentum like we did earlier. Over time, change in momentum is 1.2. Negative, if you want to put it, that's fine. It'll just come out to be negative. Time is 0.0015 seconds. The answer comes out to 800 newtons. Correct sign is important. It is newtons. The figure shows a dummy of mass 70 kilograms used in a crash test to investigate the safety of a new car. The car approaches a solid barrier at 20 meters per second. So it's at 20 meters per second. Bang! Dead stop, right? Calculate the momentum of the dummy immediately before the crash. So what's his momentum right before everything happens? So pretty easy question, IMO so far. Well, the momentum before the crash is just mv. Not change, not anything, just this. The mass is 70, the velocity was 20. This comes out to 1400 Newton seconds or kilograms meter per second. Let's move on. Determine the impulse that must be applied for the dummy to bring it to rest. Well, it's 1400 Newton seconds. That's the momentum. Change that to 0. The change is 0. Well, shouldn't that just be 1400 Newton seconds? Because you have to bring this value to 0. And if that doesn't make sense, the change in momentum is equal to the initial momentum minus the, final momentum minus initial momentum. Final is 0 minus 1400. Comes out to 1400. Well, negative, but it's just asking how much do I need, not the direction of it. How much do I need? Well, you need this much to change it to 0. Let's move on. All right, final part, not really the final part, but let's see. In the crash, the passenger compartment comes to a rest in 0.2 seconds. Calculate the deceleration of the passenger compartment. Well, the velocity was v minus u over t. The velocity is 0 now, but it began with it moving at 20 meters per second. Divide that by time in 0.2. And you should get acceleration is negative 100 meter per second square. Negative because it's deceleration or it's towards the right against our frame of reference. Either way, the answer is meter per second squared. The seatbelt and airbag bring the dummy to rest so that it does not hit the windscreen. So seatbelt's there. The dummy has an average deceleration of 80 meters per second. Wow. Calculate the average resultant force applied to the dummy of mass 70 kilograms. This is going to be again, F equals to ma. I know it says average, but that's the average deceleration anyway, right? So if this is average, this is average, right? So they're not giving us the deceleration, they're giving us the average deceleration, so we can use that. It's more not a formula, it's a common sense sort of thing, right? Okay, the mass is 70, average mass, if you will. There's no such thing as average mass. 70, because it's constant. 70, and acceleration is, well, the question says 80. This comes out to be 5600 newtons. All right, how do we answer this part? Well, so the acceleration without the seat belt came out to be 100. And with the seat belt, the average acceleration, sure, is 800. The mass of the person is 70. So the force acting on it came out to be 5600. That's what we just calculated. And over here on the left, something we didn't calculate. What would be the force if he experienced this deceleration without the seat belt? Because that's what the passenger of the car was experiencing, right? So multiply this by m, which is 70, you'll get 7,000. Right? This is what he experienced with the seatbelt, and if there was no seatbelt, he'd experience this. So he's more likely to get hurt because the force is larger if he crashes without the seatbelt. So let's put that into words. The force on the dummy is less with the seatbelt. Therefore, he is less likely to get hurt. Perfect. State why force is a vector quantity. Because it has direction and magnitude.